So my name is Laurent Lazic. I'm working in the Constellium Research Center, as you said, and which is a producer of aluminum alloys for automotive, aeronautics, and packaging. But I'm not going to talk about aluminum, and I'm going to present work I've done during my PhD with Yves in the CMAP laboratory. And that was a work funded by CNRS and ArcelorMittal with my advisor Olivier Boisiz, Rémi Diandevel, Guillaume Paris, and so Yves. So I thank them for their helps during the work. And I'm going to talk homogenization and topological optimization of architecture panels. So I'm not going to take a long time to introduce architecture materials and filling holes, but just remind the concept. First, we start with a viable material, natural materials. And here I plot a chart of Young modulus versus density. And we enlarge the space of that materials with metallurgy and chemistry, and we improve more and more that the viable materials for designing parts and products. And thanks to selection tools, we are able for a given specification and more multifunctional specification to select the good material, the best compromise between multifunctionalities. And now with material by design, we try to fill the remaining gap in such properties chart. And in terms of scale, this work deals with architecture material in between microstructures, metallurgy, thema, and structures. And here we manage to distribute the matter, mixing material or mixing material and void to get the best compromise between the given properties. And I'm going to talk about architecture panels that are much more closer than to structures than microstructures. And working with architecture and design of such materials, the problem is we have a large degrees of freedom to design how to distribute the matter, and our question was how to use optimization techniques and methods in order to help to design such material. So I will present more method than different type of architecture materials as you do during this afternoon and days. But more on methods, I mean homogenization and topological optimization in order to present a complete approach of how to, from the specification, design a given architecture panel. So I'm going to present what I'm thinking about architecture panel, and then numerical tools, and of course some prototypes and validation. So my parts will be the fourth here: architecture panel homogenization, topological optimization, and at the end an industrial case of such approach. So if we're thinking about the structures and we try to optimize a panel, such panels are usually solicited with flexion, and so the 4-point bending is the more representative test for such flexural panel. And if we use optimization, shape optimization, I will talk about that later. But if we use such texture method on this project, we will find this kind of result with putting matter in the center, where when the solicitation is flexural, is mainly flexion, we'll have matter on the skins, but in between the upper and lower indenters will more have a diagonal truss in order to provide shear stiffness. And so this is not what we are looking for, because the structure here is really linked to the position of the boundaries and the solicitation, and we are talking about a more general materials. We can put whatever the solicitation on the loadings. So we will be interested more in a periodic pattern repeated all along the panel. And so the question is how to distribute the matter in this unit cell to provide the best compromise between here only talking about mechanical properties, between bending, flexion, and shear. And so here we see that the first tool we need is homogenization to be able to compute on a unit cell the flexion and shear stiffness. So let's talk about homogenization. I'm only talking here about elastic properties, and it's more complicated when we go with damage and fracture and so on. So we are only talking about stiffness. And so still looking at the 4-point bending test, the compliants have two contributions. The contribution of bending, so here, that one. Okay, that one, and these terms for shear, and so that the bending terms, the bending compliance link the curvature with the bending moment, and the transverse shear compliance link the shear ratio with the transverse shear. And I'm introducing here the homogenization technique. We have for 3D case. We can imagine the reproduction of a 3D pattern unit cell, and this is the complete architecture material. And the homogenization step is to be able to identify an effective stiffness for this architecture materials, in order that we can compute analytically, for example, or numerically, what we want on an homogeneous 3D medium. But here we are talking about panels, so we have here our architecture panels with our unit cell with free stress boundary on the up and down of the unit cell. And homogenization step will be to convert this full architecture in effective 2D shell or plate model. The difference is that in the plate model we take into account the transverse shear, which could be neglected in some case for thin plate. So that's the shell plate. So I'm gonna first show an example for shell plate, and then we'll talk about shell, and then we'll talk about plate. So this is the problem we solve in order to identify the compliance component. So what we do, this is the mechanical equilibrium, and what we do is with a given geometry, unit cell geometry, we are applying an average here tensile in-plane force and bending moment, homogeneous, and this is done through global variables here and key that are implemented here in the strain expression, so that the unknowns of the problem are not the displacement or the strain, but the perturbation of the strain with respect to the homogeneous deformation of the unit cell. So we have here the global strain of the unit cell. It is the sum of this homogeneous solicitation and the perturbation due to the architecture. And so then, thanks to this problem, we can solve with FEM simulation. We can identify the different coefficient of compliance in tensile, in-plane tensile, and bending. So this is an example that Jean-Philippe showed this morning about embossed steel sheet. And here, so we are starting from a given hexagonal embossed structure, which give isotropic stiffness response, and we are here. We try we compute on the unit cell, so we mesh all the unit cell and just define the matter where we have of the sheet, and then try to change some parameters, and so we are able here, with a given maximum height of the corrugated shell, we are able to compute for a given thickness of the sheet. We increase the embossed height, and so here we can compare between a given straight sheet. Start from here, we increase the corrugated height, and so we have an increase of the flexural modulus because of inertia, but we lose in the tensile in-plane stiffness. And so this is the curve up to a maximum, which is when we reach the bands we choose for the height of the corrugated, and then after that the flexural Hughes modulus decrease. So one conclusion is that this type of geometry, which is capped here, is not efficient, and the best one is when you reach just the band. And then so you can reproduce the computations for different thickness, and so have this kind of chart. So enable you to design the embossed sheet you want. For example, if you want to get the same flexural Hughes modulus than a sheet with a thickness 0.7, depending on what you are ready to lose on the tensile stiffness in plane, you can then gauge your sheet from 5–10%. So that's an example of such computation. Now I'm talking about the transverse shear, and it's not trivial to apply on a unit cell transverse shear. Sorry. And so the more easy is to put static uniform boundary condition. So we put shear force on all of the face of the unit cell. But we don't really satisfy the stress-free condition on the top and bottom of the panel, and a nice formulation of bending gradient body load have been introduced by Cartreau and Lebe. And here what we do is just computing the bending solution. So applying a bending moment on the unit cell, and then we take the stress the resulting stress, and then we put it like a body force into the unit cell, and so then we can demonstrate that the resulting loading, average loading of the unit cell, is a transverse shear. And so we have a link in between the gradient of the moment and the transverse shear. So this calculation, because we already do this calculation to identify the bending stiffness, then we can do this calculation for cheap and compute the transverse shear stiffness. So now what we've done is some experimental validation on 4-point bending tests. We've prototyped some geometry of architecture. This is one of them, and so the black dots are the experiments. What we do is that we keep fixed the length here between the upper and the lower indenture, and we change the lower span. And so here, if we plot the 4-point compliance, we have this result for experiments. The points are simulation on the sample, on the complete architecture panel. So we see some oscillation due to the position of the indenters with respect to the architecture. And here the lines are the computation on the unit cell with the two calculations I presented: uniform static boundary condition and bending gradient. And we can show that it validates this homogenization calculation with bending gradients. That works pretty well. Okay, so now we have a method to be able to compute with whatever is the geometry of the unit cell, to compute the stiffness in bending, in plane bending, and transverse shear of this unit cell. So now we can go to further into optimization. So the algorithm is the following. We are starting from a given unit cell and given geometry and design. We can do the previous FEM calculation to get the effective compliance, so the performance of the geometry. At one time, we need to compute a gradient in order to minimize a given objective function that will be the criteria of the performance of the geometry, and after we have to modify the geometry. So into shape optimization, we have a lot of different discretization of our geometry, how we discretize it. We can do parametric optimization. That means that we define few parameters to describe the geometry. That's pretty simple. We have functional discretization. For example, we can imagine a function of porosity or orientation of fibers or whatever, and so you will be able to optimize with respect to this function directly. Or shape optimization with two kinds, geometrical or topological. You can create we can change the topology of that coarsening or creating holes. And so we have done such a we have used such a method in order to optimize the geometry with respect to directly with the distribution of matter. And so one of the results is when you optimize with respect to the compliance, you have an analytical result, and that say you how to change the domain in order to get a stiffer geometry. So we'll use these results. That is, we use elastic energy density as a shape derivative directly from the FEM calculation. And here we use a level set definition of the geometry. That means that we mesh all the unit cell, and through a level set function we define where we put matter and where we are void. And then at each iteration we use the transport equation with this shape derivative in order to change, to modify this level set function, and that means to change the geometry, and we calculate again the performance. So this is details on level set function and how to define the geometry with a level set function. Just quickly, that means that when this function is positive, we have matter. Where this function is negative, we don't have any matter, we have void. And so using the gradients in this transport equation, we move this equation, this surface, and so we transform the geometry. And this is a key issue, because this transport equation, and there is different transport equation, is really a big problem, and it's not trivial, and raise some numerical problems. Okay, so now we have all the ingredients for minimization of our objective function and optimization of our unit cell. We are able to compute flexural transverse shear compliance, and we introduce an objective function, a cost function, with a weight alpha in between bending and transverse shear, and then we add a constraint in order to get the same weight, because finally we want to get the better stiffness with the same volume of matter. And this is an example with a value alpha equals to 1. So we start from an initial geometry, and with 50 iteration we arrive at this simple solution to put matter on the skin. So we can show, okay, we find what we expect. So here just some discussion on the boundary we use in the transverse computation, and the computation of the transverse shear stiffness, and we show that your calculation, the way you compute your stiffness, you find different geometry, and that impact a lot the geometry. And doing several optimization with different values of alpha, so you get a continuum of optimal geometry that gives you, in this chart of bending stiffness and bending on shear stiffness, a Pareto front from the only fraction to the only shear. And you can change the constraint on the volume, on the area fraction, because we are two-dimensional. And so you have the shift of this Pareto front, and you can get a different solution. And what we see is, when we start from different initial geometry, we get pretty different optimized solution. That means that's because the problem we get is not well posed. That means that there is no unique optimal solution to this problem, and so we are dependent to the starting point. That's a problem if we want to find an optimum, but that's an advantage when we are looking for optimizing something we know we can do and we can produce. So we can start from an initial guessed geometry and then optimize around this this intuitive solution, and we'll get around in terms of topology and feasibility. And we see that all that optimized geometry are pretty much around the same Pareto front. Okay, now I'm gonna talk about an industrial case of application of such method. Here, that work was done with SMC industry that is working panels, sandwich panel for a platform offshore. And we have skin and stiffeners in inox and filled with a mineral wool. And so the specifications are impact resistance, so shear stiffness, because we are only working on the stiffeners, and fire resistance, that means thermal conductivity. So that was the standard geometry, the beginning, the actual product at the beginning of the study, and we wanted to improve it in this chart, which is shear stiffness versus normalized conductivity. So we want to go in this part of the chart. And so processing simulation of optimization from different initial geometry, we are able to propose some optimized geometry here in the centers. And then we had a regulation, a regulation step in order to be able to produce that geometry. So we simplified it because it's a constraint for the machining of such stiffener. So then, even after this simplification, we are able to propose some geometry that give a better compromise. Then we tested some of this geometry with 3D thermal calculation. The result was pretty convincing, and some tests on pretty large structures here with the same 4-point bending stiffness measurement, and also damage of the panel. And we can show that this is the previous beginning, the standard geometry. So we have a pretty high increased here in stiffness, pretty low, but also in strength. So the conclusion of this work is that we have a better understanding of the bending and shear contribution in flexural panels, and how to distribute the materials to get an optimal between mechanical and thermal properties. And we have also demonstrated how such numerical approach can be used for an industrial application. So starting from the specification and using topological optimization, how we can result in proposal for an industrial product. But we also highlight some limitations. The transport equation I talked about, which is really an issue for the level test method, and the difficulties to translate all the constraints in a unique objective function, because all the process. I talk about the regularization step we add. Of course, we cannot introduce in the numerical objective function all the constraints of the process, and that's a problem. And also, there is only few processes that allow such topological freedom we have here in numerical simulation. And we found here an application, but it's not really easy to find such a process. So my conclusion on lightweight architectural materials is that we have a high potential arising to get no compromise between properties, but of course the limitation is process for me, and also price constraint, because few of the few processes we have to produce such complex topology are really high in terms of price. And but gradient properties materials, I mean, are more and more feasible thanks to better control processes in terms of metallurgy and temperature and so long. And more and more sophisticated numerical simulation. I mean, people designing automotive or aeronautic parts are using more and more information from the process, including porosity and hardening from the previous step of the process. So then, when we control the process parameter, and when we are able to compute the results of such properties of the material into the final part, then we are able to optimize and to propose graded materials like we've seen. And a key conclusion also is integrated development. There is a trend to co-develop alloys and the product design together from the early stage, and not separately. People that design a car or in their side, and we are designing alloys in our side. So there is more and more work together, and so this enables the possibilities of improving multifunctional performance and improving such architecture solution. Okay, and that's conclusion on shape optimization. Okay, I'm not going into details, so thanks for your attention.